All right, so let's continue our discussion of all the things we can do with the Riemann tensor and develop any other tensors that are of interest in the spacetime. And the first thing to keep in mind is that really this is the big cheese tensor, right? This guy, it's derived from the metric, right? The metric goes through the metric connection. Let's see, A, B, C, like that. And A, B, C, and the metric connection gives you the Riemann tensor through the analyses we did before, either geodesic deviation or moving a little vector around a loop. But everything is embodied in here that really tells us about how curvature operates in spacetime. Ultimately, it's all the metric. And the metric gives us the connection gives us the Riemann tensor. But of course, you can write formulas that go straight from the metric to the Riemann tensor. All of these things depend on each other. If you set one, you'll get all of the others, with the caveat of being in a torsionless spacetime. Torsion-free is really the only way I've done this analysis myself. But so other tensors that we can develop for our manifold that are related purely to the geometry of the manifold, ultimately they all have to come back to this guy. They all have to come back to the Riemann tensor. So, for example, the Riemann tensor is a 1-3 tensor, and we know that we can always take any tensor and automatically contract indices. We can create contractions, which, remember, are maps from contractions are maps that lower the rank of each of the slots by 1. So this would be a map from 1-3 to 0-2, right? 1 minus 1 is 0, and 3 minus 1 is 2. So there's a 0-2 tensor out there that's canonical in the sense that it's just a contraction of this guy. Well, in fact, there should be 3 of them, right? Because there's 3 possible contractions. We can have our, let me get out of red here. We can have our sigma alpha beta. We could have R sigma nu sigma beta, or we could have R sigma nu alpha sigma. So it's going to turn out, however, that this one will equal 0, and these two will just be different by a factor of -1. So ultimately, there's really only one contraction. And all of that can be traced to the fact that R mu nu alpha beta, right, that it's antisymmetric in those two indices and it's antisymmetric in those two indices. So we can write this as R, it's equal to its antisymmetric part, mu nu alpha beta. And this we talked about in our last lesson is how this is actually the tensor product of 2 bivectors, which I think we'll have more occasion to discuss later. But the combination of this and the fact that the metric tensor, G, say, alpha mu, is equal to G mu alpha, meaning that the metric tensor is symmetric, that's what gives us this fact, right? Because I can start with R mu nu alpha beta, and I can contract it with nu mu, right? And what am I doing? I'm contracting this, which is symmetric, into an anti-symmetric object, which is nu mu, right? That's anti-symmetric. And so this guy is going to be 0, right? And likewise, if I went with R mu nu alpha beta, I say that's minus R mu nu beta alpha, and then I just raise indices on both sides. I say G alpha mu, say both sides G alpha mu, then I get R alpha nu alpha beta, which is the Riemann tensor, right? That's going to be, we'll call that R nu beta. But on this side, I'm going to get minus r nu beta, right? Because what happens is this elevates this mu to alpha, and that alpha contracts on the third one. So you end up with nu beta left over, which is the nu beta right here. And so this is the opposite of just of this regular, which is going to equal the opposite of, say, sigma nu sigma beta, right? So if I can, in other words, if I contract on the middle two, I just get the opposite if I contract on the first and the last. If I contract on the first and the second, however, it's zero. So the point is there's only one real contraction, and that contraction is the Ricci tensor. R nu beta, that's called the Ricci tensor. And the Ricci tensor is defined with this guy right here. This guy right here is the Ricci tensor. It's the middle contraction, contracting over the middle two. And that's really a sign convention, right? Because the contraction over the first and the last is just as legitimate, right? So I could have defined it that way. And so your choice of this is a sign convention in your system. But almost every reference I see actually defines it on this, the first index contracted with the middle index. So that's the Ricci tensor, really, really important tensor. The Ricci tensor is really important. I'll just give you a hint why it's important. We've already said that the curvature is pretty much it's entirely embodied by the Riemann curvature tensor. But we also know that the distribution of matter in space-time is governed by another tensor, say delta gamma, and that's called the stress energy tensor, the mass energy tensor. And this tensor tells you how matter is arranged, how all energy is arranged, electromagnetic energy, matter. It's all arranged in space-time, and this tensor is the way to describe it. And it turns out this tensor is symmetric. We'll spend a lot more time on this object in a future lesson. But, it's a legendary object in physics, and it's critical in understanding general relativity. But this tells you where matter and how matter is positioned throughout space-time. When I use matter, I mean all forms of energy. But so if you have a theory where you want to say, hey, matter is responsible for curvature, somehow I have to say, okay, ultimately I have to be able to draw an equal sign between these two things with some unknown junk in front of this, right? And it's got to be a tensor equation, right? The presumption is that it's a tensor equation, because that's sort of what general relativity is all about. Everything's got to be a tensor equation. And so we have to make this connection, and we have to sort of find something to go here. The problem, of course, is that if this is a rank 0,2 tensor and this is a rank 1,3 tensor, you can never have an equality between the two, right? You can't, 1,3 tensors just don't equal 0,2 tensors unless there's another tensor here and this equation is actually a tensor product, right? So, what tensor could you possibly put there? Well, there aren't too many choices, but given that the space-time is entirely defined by this guy, well, we've just discovered a tensor. We've discovered the Ricci tensor, so maybe I can do the Ricci tensor. I could put that there and make a tensor product on the right-hand side. Or the metric is always available, right? The metric, you can always use the metric in these things. That could go there. And then if I made this a tensor product between these two, I could get, well, if I did that, I would get a 0,4 tensor. But if I raised one index, I could match it. Or if I lowered this index or something. So you have to do something like that. You have to get both sides to be the same rank. Or you could work on this side and you could say, hey, what about this? What about R alpha beta equals something T alpha beta? And that says, hey, it's not that the curvature tensor equals the matter distribution. It's this part of the curvature tensor which equals the mass distribution times some factor. And that would make sense. It turns out this is a symmetric tensor. So whatever is on this side would have to be a symmetric rank 2 tensor. And sure enough, that guy is a symmetric rank 2 tensor. So let's prove that. The way that works is using yet another identity. It was this identity. Remember R mu, let's see if I did do this right, nu alpha beta, anti-symmetrized. The last three of these guys are anti-symmetric. That has to equal 0, right? That has to equal 0. And that's just like, and so we can imagine then raising, so I can write this as G alpha mu. Let me just write it out, right? If you expand this anti-symmetry, and then you end up with three positive parts, but you also end up with three parts that come in with a negative sign. So there's 6 terms in this altogether. But of those 6 terms, remember, there are anti-symmetries in these indices here. And so if you flip them, those negative terms, the terms that come in through this anti-symmetric symbol with negative signs, they flip signs and then they add together, so you only have 3 really substantive terms. And then you end up with these 3 terms equal 0. That's why we can write this equals 0, and what you're really saying is these 3 together equal 0, despite the fact that when you blow this up, literally, you don't get this. You have to then flip a few indices, change some signs, and then recombine, and you ultimately get this. But once you've done that, then you introduce this guy, right? So you raise mu and you convert to alpha. So in this case, you're going to create the Ricci tensor, right? Because you're going to have an alpha in the contravariant slot. And then in this case, you're going to have the alpha in the contravariant slot, but you're going to be summing over the first 2, which we've already shown is 0. So this term will go away. And then this goes over the third slot, and that is equal to the opposite of what you get here, right? So those 2 will cancel. And so this will literally equal 0. But on the way to equaling 0, you get, okay, so we've taken the Riemann curvature tensor, contracted over these indices, and we've got the Ricci curvature, the Ricci tensor. And then, of course, you can do the same thing one more time. You can then take this tensor and create G beta nu R nu beta, and you end up with R, beta beta, which is the definition of the curvature scalar. So that's another object that flows forth directly from this. And once you've chosen the sign convention for this guy by establishing that you're going to use the middle 2 as opposed to the by establishing that you're going to do the contraction over the first and third index instead of the first and fourth, then this is established in the same fashion. So this is another number that flows forth from the curvature all the way. And now this is all the way through just a forced series of transactions, a forced series of logic. It's canonical, right? It's canonical. If this exists, then this must exist, right? And if this exists, then this must exist. So these are the canonical objects. And you end up with this guy, the curvature scalar. Now, the intuition of what these things are, that deserves a whole separate lecture, and so we are not going to do that now. We are now understanding sort of the mathematical formalism of it. And being canonical has been very important to me in these lectures, and I always emphasize it. So we have this. Once we have I guess why not just make it all completely present here, right? I can just say once we have the connection, and once we have the metric, connection, curvature, once we have the curvature, we have the Ricci tensor. Once we have the Ricci tensor, we have the Ricci scalar. So all these things flow from each other. All right, now we are going to do the hard one, and that's called the Weyl tensor. So this is the first part of our introduction of something called the Weyl tensor, which definitely is still part. It still flows forth from the Riemann tensor, right? The Riemann tensor is basically equal to the Weyl tensor plus another piece. And it's essentially a way of decomposition. You can think of it this way. Decomposition of the Riemann tensor. Here, we didn't really decompose the Riemann tensor. We just followed some known maps. This was the contraction map, and this was a map from... Okay, so this is a contraction mapping from here to here. The mapping from here to... this mapping here is, well, it's another contraction mapping, essentially. You've got to raise an index and then map. But either way, it's a contraction mapping. Well, it's two maps combined. It's a mapping from the 0,2 tensor product space to the 1,1 tensor product space, followed by a contraction, right? So they're canonical maps. This is a little different. We're now going to talk about things that are look like this. R mu nu alpha beta equals C mu nu alpha beta plus other things, right? And those other things plus this is a form of decomposition. And we design these decompositions so that this has certain properties and this has certain properties, and everything is equal by tensor formulas. So the Weyl tensor isn't something you can create literally out of the Riemann tensor. It's something when you have a Riemann tensor, if you split it apart in a unique way into two other tensors of the same tensor product space, right? Remember, this is 1, 3. So every term on this side has to be a 1, 3 tensor, because this is your sort of vector addition property. And of course, we're doing this all in the components, right? We've abandoned any pretense of writing down R mu nu alpha beta with tensor product dx nu tensor product dx alpha tensor product dx beta. This is true, and I always keep it in mind. But as I promised, is this I emphasize so much in the What is a Tensor lecture just to help us understand what was going on. Now we're throwing that away, and we're using the ordering of the indices to keep track of what tensor product space we're actually in. But this is a tensor equation, right? So this guy here has to be in the same tensor product space as this guy, and so does all this other stuff. This is what we're going to call the Weyl tensor, right? It's going to be one part of a decomposition. So what we're going to do here in part 1 is we're going to talk about what kind of decomposition we want. And there's really two ways to approach this concept. So let's look at how we might do this. The Riemann tensor will be broken down into this guy here, which we're going to call the Weyl tensor. Sometimes it's called the Weyl conformal tensor. And that's the word conformal tensor is going to be the big deal I'm going to try to introduce in this lecture. And then there's a remaining piece. And how do we distinguish between what is a part of the remaining piece and this guy? And we do this by establishing basically the rule that we want this thing to behave. And how do we choose this rule? Well, we choose this rule because evidently we've studied this very, very, very carefully, compared this with other forms of physics, and we came up with this interesting idea. And when I say we, I mean Weyl. Weyl came up with this interesting idea. And of course, caveat again, I'm not a historian of physics, but these are the narrations that have come down to me in the time that I've read and learned about all of this stuff. But what Weyl was very interested in was, if I have a metric on the space-time, and I'll write it in sort of this boldface notation, right? And I take that metric and I multiply it by some arbitrary function, which I'm going to call e to the I pi of x, right? So this is a function on the space-time. The e keeps everything positive, so no matter what the sign of this arbitrary function pi of x is, this guy's positive. Another way of saying it often is omega squared g. So this guy omega squared is always positive. We're actually going to use this form. But if I take g and I create a new metric, right, a new metric that is conformally related, then these two guys are very closely connected. The only difference is this function on the space-time. So remember, g itself is a function of the space-time. So if you give me a space-time point, I will be able to give you the components. This is the bold version, right? I will be able to give you the components g mu nu at that point in space-time. So I can tell you g0, 0 at point x0. I can tell you g 1, 1 at point x0. I can tell you g 2, 3 at point x0. I can do that because once I know this is a formula, right? And so if I take all of these calculated position values of the metric, right, for every pair of indices, and for diagonal metrics, you know, these many terms will be 0, but in full generality, it doesn't have to be the case. But if I take them all and I multiply them by e to the pi of x, where pi of x is a function smooth on the space-time but arbitrary, right? I'll get new values, right? These are going to be numbers. These are going to be numbers. And this is going to be a number. And this is going to be a number. And when I multiply this, these numbers are all going to change, right? So the metric is actually different. But at every point in space-time, then each component is just, every point in space-time is just going to be different by a factor. The problem is this is a function on space-time too. So the factor that the metric components are multiplied by changes at every different point in space-time. So it's not a totally trivial. It's not like simply taking the metric and multiplying it by a number. You're multiplying it by a function on the space-time. However, it is still a limited change of the metric. And in fact, it's called a conformal transformation. This is called a conformal transform. This guy here. So what Weyl was very curious about was what happens to the Riemann tensor under a conformal transformation. And the answer is it changes, right? The physics of the world changes. And by physics, we mean the curvature of space-time, right? Because that's what we're aiming for. The curvature of space-time does in fact change if you execute a conformal transformation of the metric. But I guess what he did is he asked, there must be a piece of the Riemann tensor that doesn't change when you have a conformal transformation of the matrix. It's a little unclear what motivated, well, it's unclear to me what motivated him to be worried about that. It's definitely true that in quantum mechanics, if you write e to the I pi of x and you multiply your wave function by e to the I pi of x, nothing changes, right? Your predictions of your theory are exactly the same. And that's because you end up always expressing these wave functions against their conjugates. So you end up with another one that has a minus sign in there, and these guys always cancel. So the wave function has this sort of arbitrary factor that you can add in front of it, and it's called gauge. It's, you know, we'll be talking about gauge transformations. So he was interested in that in the context of general relativity. So he wants to find a piece of this guy that does not change under a conformal transformation. Okay, so how do we think about this mathematically? And we're not going to go too deep into it this time. Next time we will complete the entire proof, but let's get it started. So I begin with the actual core of the transformation. The metric is changing by this conformal factor. And then I'm going to say, well, what is the variation of the metric under a conformal transformation? And the definition of that guy is going to be G hat mu nu minus G mu nu. And so the way I treat this is this variation is going to be for a small conformal transformation. So we're going to deal with a small version of this. So how do we do a small piece of e to the pi x? This is one of the reasons why the e to the pi x notation is a little bit more straightforward to me, is because that its approximation is clearly 1 plus, let's see, how do we do it? 1 plus epsilon pi, plus higher order terms in epsilon squared of G mu nu. In other words, when pi x is made small by multiplying by a factor epsilon, I can then approximate this whole thing with just 1 plus e pi, 1 plus epsilon pi G mu nu. And what that's telling me is that my G hat mu nu, the infinitesimal transformation, looks like this. So this guy here in the infinitesimal transformation looks like that. And then it's pretty easy to write G hat mu nu minus G mu nu, and that becomes epsilon pi G mu nu, right? Just expand this guy out, subtract. So this equals the variation in the metric. So this is the variation of the metric for an infinitesimal transformation. Notice I've gone from pi of space-time. I just write it as pi now because this becomes really messy, and my handwriting is already a problem. But putting those x's in there, you just need to know whenever you see pi, that's a function of space-time. Epsilon is not. Epsilon is just a small number. A small number. It's how small? It's so small that this epsilon squared can be ignored, right? That's your typical way of linearizing exponentials. And now it is worth your while to convince yourself that G mu nu, the fully contravariant form of this thing, is going to be 1 minus epsilon pi of G mu nu. It's because they're inversions of each other. And so the inversion basically drives a minus sign up here, right? And therefore, the variation, the infinitesimal variation of the contravariant form of the metric is equal to minus epsilon pi G mu nu. Like that. So you have these two forms that represent these variations of the metric under infinitesimal transformations of this form. And infinitesimal is always important because when you do that, first of all, actually though for this mathematics, you can actually use the fully finite transformations without much trouble. But what we're trying to do is we're going to execute a transformation of this type, a conformal transformation on the metric. And that is going to cause, so once we start with our metric, we do a conformal transformation, which is going to give us a variation in the metric. And that variation in the metric is going to flow through everything. We're going to get a variation in the connection, which is going to give us a variation in the Riemann tensor. I'm using R mu nu alpha beta, which is going to give us a variation in the Ricci tensor, right? Nu beta, which is going to give us a variation in the scalar. All of these things are going to, once we start with this transformation here, this conformal transformation, right? Once we begin with that, everything's going to have a variation under it because everything depends on the metric. Everything flows from the metric. So we know a formula for this in terms of the metric, so we'll get a variation in this. We know a formula for the Riemann tensor in terms of the connection, so a variation in the Riemann tensor can be calculated from a variation in the connection. And these guys are directly related to the Riemann tensor, so those variations can be calculated. we're not going, these expressions are quite complicated. I'm going to do this one. I'm going to show, I've already done this one, right? I've shown that if we do a conformal transformation of this type on the metric, we end up with this guy, which is here and here. I'm going to calculate this one just to show you how smart I am. But I'm not going to go through these because these are it's just a huge mess. I mean, this is messy enough, but these are even worse. But ultimately, it's just a bunch of algebra. There's nothing super insightful or clever. It's literally just a bunch of algebra. So we'll do this one. Now, the idea ultimately is once we do a conformal transformation on all of these things, we can go back here and we can use that conformal transformation to find a part of the Riemann tensor that does not change, that does not change under conformal transformation. And so we're looking for something where the C mu nu alpha beta equals 0. We're looking for something where the infinitesimal variation of the Weyl tensor will be the part of the Riemann tensor that has no variation under this transformation here, right? And that transformation is just that important, right? We've actually studied conformal metrics earlier when we talked about coordinate systems and doing conformally related coordinate systems. This is one of our earlier lectures in the GR series. But this is important enough that it's worth breaking down the Riemann tensor into the part that has no variation under a conformal transformation and a part that does have variation under conformal transformation. So we'll get into that in our next lecture, but right now let's calculate this guy. So we begin by writing down what is the definition of the connection, the metric connection in terms of the metric. And this is it. We worked really hard a long time ago to prove this. So now we're going to look at what is gamma hat alpha beta mu, meaning we execute the infinitesimal conformal transformation. This is going to change a little bit, and what it changes into is this thing. So what is that expression? Well, we're going to substitute the infinitesimally transformed versions of each of these metric components into its transformed version, which is going to be, in this case, 1 plus epsilon pi g mu nu. So wherever I see g with two indices, I'm going to replace it with this. And wherever I see this guy, I'm going to do the same thing, but I'll have a minus sign there. And so that's how I'm going to calculate this guy. Okay, so here I've done it. This piece here is replaced by its infinitesimally transformed version. This is replaced by its infinitesimally transformed version. So now we have to understand this differential operator, it's acting on this whole thing, right? So you could almost put braces right here, right? Same here and same here, right? So this here has been replaced by 1 plus epsilon, 1 plus epsilon. Notice the minus epsilon here because we're dealing with the contravariant form of the metric. And so this is the transformed version. And so now we're after the calculation of the variation of this. That's how much does this change when you make this transformation, right? And that's going to clearly equal to the changed part minus the unchanged part, right? So I basically have to take this, expand it all out as best as I can, expand everything out, and from that subtract this. Now notice, remember, pi is a function on space-time. This is really important. All this notation can get to be quite confusing if you're not tracking completely. So partial mu, right? This is d by dx mu, right? That's what that means. So this means, forgive me if this is too elementary. I know at this point this should be second nature, but if it isn't, this is a derivative with respect to space-time. So that's reminding us that g sigma beta, for example, is a function of spacetime. So taking the derivative with respect to a spacetime of that certainly makes perfect sense. This here is also a function of spacetime because I'm having you remember that pi really means pi of x, a function of spacetime. That goes back to this right here where I said, look, that's a function on spacetime, right? And so this could be written a different way, right? We could have written this, right? We could have written it as, or we could have written this up here. We could, instead of writing g or partial mu g sigma beta, I could have written g sigma beta single line mu, right? But then when I change this, I would have had to change it by writing 1 plus sigma pi, right? And I would have had to emphasize that 1 plus sigma pi, and this, that's where I'm taking my single partial derivative of, right? So I guess the way to say it is this: 1 plus epsilon pi g sigma beta. I can go either sigma mu of the whole thing and then make sure I put brackets like that, or I could put brackets like that and then put a single line. Wait a minute, sorry. Hold on. Okay, this is what I mean. This term here, which is right there in our system, this term is supposed to mean the partial derivative of everything off to its right. So you can actually put brackets here so you don't mistake it as thinking, oh, it's just the derivative with respect to this space-time function, but it's the derivative with respect to the product of this space-time function here and that space-time function there. So you could write it this way. The alternative notation would be you still kind of need the brackets, and then you put the line mu here beyond the whole thing. The problem is the ambiguity is that this form's ambiguity is what is subject to to this derivative. Is it this whole thing or just this first thing? In the second case, if I had gone up here and used this alternative notation here, g sigma beta straight line mu, and this would be g sigma mu straight line beta, for example. If I had used that notation, then I would have had to adopt something like this once I executed the transformation. So there's always a little bit of an issue one way or another. But the point is regardless of the notation, which I got to say I do find quite fascinating, despite its being like the least interesting scientific idea here. But ultimately, we need to just take the difference. We need to subtract from this. So there's a little good news at the front end, right? We're trying to calculate delta, or the variation alpha beta mu, which is hat alpha beta mu minus gamma alpha beta mu. So if you look at this minus this, right away you see that there's a piece of this that will completely cancel with everything there. And that piece is this first part here, right? If you distribute out this factor, the g alpha sigma, and you distribute it out here, you'll notice that it'll match g alpha sigma factored out from this differential here. So like this expression right there is going to equal partial mu g sigma beta plus partial mu of epsilon pi g sigma beta, right? Where that's all clustered together. So that's what this term here equals. Then this term here, right, likewise is going to be partial beta g sigma mu plus partial beta epsilon pi g sigma mu. Right, that's what that term here is. Let me just erase that little line there. Partial. And then this last part will be minus partial sigma g beta mu minus partial sigma epsilon pi g beta mu, like that. So these three terms will replace these three, and then they have this factor in front. So the g sigma, the simple g alpha sigma factor coming from this first part is going to multiply all of these three. So if you ignore these and you just take the multiplication of this with these pieces here, you basically duplicate that, and they all cancel, right? So this whole thing here, basically this, will cancel with this, and that whole piece. So what remains is calculating what's left, meaning we got to calculate essentially everything here and all of the parts that don't involve this one. Everything else is canceled. So what remains after we do that? I got rid of those little red lines on the ones because we will need them for the calculation of the second piece of this term. So what remains after everything's canceled? Well, let's see. All right, this is what we end up with, right? So we get this. Let's see, which one is the more logical one to do first? Let's see, if we go back here, we see that we still have this, let's see, we have this minus epsilon g alpha sigma, right? And it's got to be multiplied by the partial derivative of just the metric part, right? That's this sort of first piece that includes this one when you distribute through this one. So it's the partial derivative of just that metric part. So that's what this is, right? It's the g alpha sigma, and then it's just these partial derivatives. And you'll notice I'm using the line notation here just to compress things a little bit. And here for the second term, I use the other notation just to mix it up a little bit. It's okay if you understand, if you know what these notations are, it's okay to use in the same expression two different variations. I mean, this is understood to mean this. There's a reason I'm doing this, is because I want to capture the fact that it's the derivative of that whole thing, this is where I could have done that instead, right? But I just didn't. This time I did here. These are the partial derivatives. I could have put that in there instead. I like doing it just to keep everybody on their toes. So here we're actually mixing it up a bit. So that's what this first term is, right? The second term is actually this part here multiplied by the derivative of this part here, right? And so that is going to be what this expression is, right? If you kind of in your mind, put in these parentheses like this, right? You end up with that term. Now the last term, that's this guy here, you'll notice that's this piece here, this with that minus sign, multiplied by this piece here, we've already done. But the problem with that is you get these two epsilons, so you get that epsilon squared. So that part is always a factor of epsilon squared, so we just eliminate it. We don't even consider it. So you're only left with those two factors, which in the limit of small epsilon represents sort of the linearized conformal transformation. So now what remains to do is we could do a few different things. We can take this and use it to raise some indices, but probably not interested in doing that right now. But these have to blow up, because remember, this is what I'm saying is the partial derivative. I can take the epsilon out because that's just a number of one function of x multiplied by another function of x, where x is space-time, right? And so I can now write this as the partial derivative of that with respect to x mu. And these guys are functions of x, alpha. So that's what these guys are. So they need to be blown up using the product rule. So for example, this term here, partial mu, well, epsilon partial mu pi g sigma beta is going to be epsilon times partial mu of pi multiplied by g sigma beta plus pi times g sigma beta partial mu, where I'm using again the mixed derivative form. All right, let me not do that. I can just see that that's going to be a problem for somebody. Pi partial mu g sigma beta, right? That's going to be this term. And all of these terms are going to have the exact same expansion and structure. It's simply a partial derivative. So, but I will actually clean this up a little bit notation-wise, and I think it would make sense too. All right, here's the equivalent notation using the this little line, subscripted line thing, right? This is a function, derivative, partial derivatives with respect to mu, and this is, again, the function's partial derivative with respect to mu. So this expression and that expression are the same, this expression and that expression are the same. So once we've agreed to that notation, we can now write another form of the expression. What we can do is we now simplify this. We simplify this. And what you're going to get now is that the variation in gamma, these three terms blow out, right? These three terms, once you expand, so you have this term already, and this guy's going to blow up into two separate combinable terms, and that's this one here that contains these derivatives of pi, and this one here which contains pi times the derivatives of g, right? And this will cancel completely, right? And leave you just with this, right? So that is going to equal the variation of gamma, alpha, beta, wait a minute, how do I write it? Alpha, beta, mu. And that's the final expression. So the final expression only contains the derivatives of this, we'll call it gauge function. Oops, I'm missing a derivative here, of course, right? This should be a little line right there, right? I just added a line right here. So this is it. This is the answer. This is the variation in gamma. So given the variation of the connection, so given the fact that we do an infinitesimal variation of the metric tensor, we're led to an infinitesimal variation of each of the components of the connections. That's what this thing is, right? An infinitesimal variation of the components of the connection is given by this expression. And it's driven to be infinitesimal because you've got this e here, so you know that small enough e, you can make this arbitrarily small. That's very important for a variation. But these derivatives of pi is unrestricted. And the derivative of pi could be huge, right? You know, derivatives can be of any size and any sign. So now this can be simplified a little bit, right? We can actually raise the sigmas here on this thing. Yeah. So so in other words, I can take this and I can move it inside. I can distribute it inside and get a simplification based on the properties of the metric. Let's do that. That is, so starting with this expression where I've put the metric tensors first and then the derivatives of pi, the gauge function second, or the conformal transformation function second. Here I had it the other way around, right here. And I distribute through with this. You'll see that what I'm going to do is the distributing is going to effectively raise alpha. It's going to raise sigma and convert it to alpha in every one of these cases. So here you'll end up with alpha there, you'll end up with alpha there, and you'll end up with alpha there. And you've got to remember that G alpha beta equals delta alpha beta, right? That's, I'm sorry, I'm sorry, think of it this way. These guys are inverses of each other, so they end up equaling this delta function. Therefore, this whole expression simplifies a bit, and it's left in this form. If you decide to do that, you end up with this form here, where this is pretty easy and that's pretty easy. This becomes a bit of a confusion at the end because G alpha sigma is raising the index on pi. So you may remember pi is a function. So the covariant derivative of pi sigma is just equal to its first derivative, right? Because in functions, the covariant derivative and the regular partial derivative are the same. So you can actually, so this counts as an index that can be raised, so this does as well. So I could write pi line sigma like that. I don't think I've ever seen the notation pi line sigma like that with the upper part. But regardless, what this means is it means G alpha sigma of pi covariant derivative sigma, right? And that's what we mean by pi covariant derivative alpha, which, I mean, this is this means, I'm sorry, undo. This means pi covariant derivative alpha in the upper position, which is also the partial upper derivative of pi, like that. It's kind of a messy little, well, it's not messy. I mean, it's a totally normal thing. This is a regular index that can be raised and lowered. But the trick to understand is you might be tempted to say, well, wait a minute. I guess the pitfall is you might be tempted to say, well, wait a minute. The regular partial derivative, that's not a tensor. But it is a tensor if the object that's being, the derivative of which is being taken is just a function. If it's a scalar, then the partial derivative and the covariant derivative are in fact the same. So you can raise that index. So this makes perfect sense is what I'm getting at. Okay, so this is the variation of the connection, right? That's what this is. This is the variation of the connection. Let me clean up this back part. So now with the variation in the connection, you can now calculate the variation of the Riemann tensor, right? We're now looking for the variation of the Riemann tensor, mu, nu, alpha, beta. That, you can imagine how hard that'll be, right? Because we have to go back to the definition of the Riemann tensor in terms of the connection, and then we have to write the Riemann tensor's infinitesimal variation minus the Riemann tensor, right? That's going to equal this variation. So I have to make the full-on substitution in terms of this guy here, and, well, the full-on substitution between the two. Yeah, in terms of both of them, in both places, I have to use this variation to get these two terms, and then I have to subtract. It's a big mess. And then once I have those, then I have to calculate R, A, B, and the variation in R, right? So fortunately, this has already been done, and I will write the answers out right here just so you can see them. So for example, the variation in the fully covariant component form of the Riemann tensor is given by this expression. You'll notice that every term has an epsilon, so variation goes to 0 as epsilon goes to 0. You have the, what I'm calling the gauge function, but it just sits there as a product of the original Riemann tensor. And then you add all these weird little terms on it. And, you know, this is what comes out of that calculation I just mentioned before. The thing to keep in mind is there's a lot of ways of writing down. So pi covariant derivative, second covariant derivative, beta nu, right? Well, that is actually, think of it this way, pi, second covariant derivative beta, right? Second covariant derivative nu. But this guy I told you is equal to its first partial derivative. So that is pi partial derivative beta, second partial derivative nu. And sometimes you see it written that way, pi 1 beta 2 nu, right? I've always seen it written this way, right? So for what it's worth, but But just be aware, this notation does appear, and it looks a little confusing, but it really only works if pi is a function. If it's any kind of other tensor, then you've really got to be careful with this stuff. Then the expression for the variation of the Ricci tensor is given by this little thing. Here again, you see that it's a function of epsilon, so the variation goes away as epsilon gets really small. Then you have this fully contracted part right here, right? So that can be understood as just as a function all by itself, meaning it's fully contracted, so there's no indices left on that. So the only indices that matter are these two, right, mu and alpha. And over here you have the two indices mu and alpha as the second covariant derivative of pi. What's interesting is you end up with this number n. And a lot of work that has to do with the Weyl tensor keeps this number n. And that n is the number of dimensions on your manifold. Number of dimensions on manifold. Now in general relativity, n always equals 4. But they love to point out, or eventually we like to point out, that the Weyl tensor disappears and reappears for certain numbers of dimensions. So a lot of the formulas keep that n in there. But you might be asking, well, how does it get in there to begin with? How do you end up counting dimensions? And it's because you end up with terms that look like this: G alpha beta, G alpha beta. The fully contracted form of the metric tensor ends up equaling n, the number of dimensions. And you can kind of understand that, right? You can see how you're basically going to end up with -1 times -1 plus 1 times 1 plus 1 times 1 plus 1 times 1. You can work that out yourself. Work out that double, if you don't know it already, but work out that double contraction and you end up with 4, right, for regular space-times when you have Minkowski metrics involved. So that's the variation of the Ricci tensor, right? And so all that's left is the variation of the curvature. And this is what I have for this. By the way, all of this comes from a certain paper that maybe I'll put this paper in the list of available papers for the course. Let me write out this paper that a lot of this came from. This is the website of a man who really digs Hermann Weyl. And I can understand he's a really interesting guy. The man specifically is Mr. Straub here, who I have not met, but clearly he has his priorities in the right place. And if you go to this one, and then I think you need to go to conformal.pdf. Yeah, that's it. Then you'll come to the paper that I essentially ripped off that entire analysis from. It's a good analysis. The way I learned it was to force the trace of, to find something back here. Where was that original statement? To find the trace of this was equal to 0. I remember my initial experience with this was to prove that the trace of this guy was 0. This approach that Straub prefers, and I think is actually much more interesting and probably more informative in the end and more relevant ultimately, is to show that that we're looking for the piece where C mu nu alpha beta, the variation of that under an infinitesimal coordinate conformal transformation, is 0. And so that's what we're going to prove. So we're going to next lesson use these three things together combined to find a value of C that gives you 0 variation under conformal transformations. And it's worth it because C is what separates, I would say, maybe it separates intermediate general relativity with advanced general relativity. So it's definitely worth knowing if you want to push on and getting a good feel for this thing. it shows up in intermediate general relativity, but regardless, it's part of what curvature is. It's part of the Riemann tensor. I think there's a way of formulating almost all of general relativity via this tensor, and throwing away the rest of it. It doesn't work universally, of course, but I think it does apply under certain really interesting circumstances. Gravitational waves is definitely one place it does, but I think it has even broader validity than that. Okay, so next time we are actually going to derive the value of C that makes this variation 0, and then we'll have yet another tensor to add to our list of tensors here that can be derived from the Riemann curvature tensor.